In the last few lessons, I've been trying to give you information with which you can get started with force curve acquisition. So we've looked at the basic shapes of force curves, the processing involved, the probes that you might select, the problems that you typically run into, and here in lesson 23, we'll be looking at background information, some vocabulary, work of adhesion, contact radius, reduced radius, stress strain, elastic modulus, and Poisson ratio. And that's all to prepare us for the meat of this unit on force curve interpretation, and that is the modeling of force curves. Imagine you had a perfectly flat cylinder and you were able to bring it down perfectly perpendicularly to a surface and put those two things in contact. If you then separate those two, then the amount of work that is done as you separate them from contact and take them out to infinity per unit area is known as the work of adhesion, omega bar. And that's measured in joules per meter squared. Be careful of this. It says work, so you would think it would just be joules, but implicit in the definition is that per unit area. So to write it out mathematically, we'd say work of adhesion is equal to the work done, which is the integral of the dot product of the force and the displacement per unit area. We will use this as we talk about attractive forces and how they affect force curves. But most of the time, we do not have a perfectly flat cylinder in perfect contact with the sample surface, because that's too hard to do, to bring down something perfectly perpendicularly. So we usually have some kind of rounded end to our tips, and even if they're not wholly spherical, the end is usually modeled as a hemisphere. It indents to a depth delta. It has a radius r. And we want to know what the contact radius is because we would like to be able to predict the contact area. And this is usually done in this fashion, that we say that this distance here from the central axis out to where tip and sample lose contact is the contact radius A, not this distance here. So it's like the projection on a horizontal plane. In order to find that contact radius, we make use of Pythagorean theorem, and also the fact that the height at which the tip and sample lose contact with each other turns out to be half the indentation depth. That one is tricky to explain, so I'll just ask you to accept it. And now we can say this distance here is r minus delta over 2. And so then Pythagoras tells us that r squared is equal to r minus delta over 2 squared plus a squared. And the quantity becomes r squared minus 2r delta over 2 plus a squared. And cancellations here and here. Oh, you know what? And I forgot a delta squared over 4. And so a squared is equal to r delta minus delta squared over 4. Now, frequently, although not always, the tip radius is much larger than the indentation depth, and that means the second term is small. So in many cases, the contact radius is approximately equal to the tip radius times the indentation depth, square root. And when we're thinking about contact, we should think about how the topography of the sample can influence the contact radius, and for that we need to know what the reduced radius is. A reduced radius, well, it's sort of like adding resistors in parallel. You add the inverses of the radii of the tip in the sample. So for our familiar case of the tip coming down to a horizontal sample, we would have 1 over r for the tip, but then 1 over infinity for the sample. Horizontal sample has infinite radius, and of course we can ignore this, and so our reduced radius is not a surprise. It's just what we expect. The radius of the system then is just the radius of the tip. Let's apply this to a tip coming down on a bump that is the same size as the tip. And so we get 2 over r for our inverted reduced radius. And then we invert that, and our reduced radius is half the radius of the tip. And then here, when the tip comes down into a valley, we've got 1 over r for the tip, and then minus 1 over 2r for the sample's valley. And then we multiply this by 2 over 2, which is 1. So we get 1 over 2r here. And then we invert that, and we find that the reduced radius for this case is 2r. Now, what about the bulk properties of your sample? Well, there are things called stress, strain, and elastic modulus. Imagine you had a big sample that about a size of your finger, and you were doing a tension test on it, such that you grab the top and bottom of your finger and pull. And you watch to see what happens. The kind of plots that one generates is stress on the y-axis and strain on the x-axis. Well, stress is force per unit area, so your cross-sectional area of your sample, and strain is the change of the length of the sample over the original length of the sample. And how most materials behave is the following. There's a linear region, and then it starts to bend over, and then it might break about there. And that linear and reversible region is the elastic region, and the slope of that region is the elastic modulus. So that is the stress over the strain. So modulus has the same units as stress, which is newtons per meter squared, or alternatively pascals. I'll also add that if you go beyond the initial linear region of the stress-strain curve, and then maybe come up to this point on the curve, and then release the load, that it returns not to the origin, not to the original length, but to an extended length. And so in that case, we say that the sample has undergone plastic deformation, meaning that it has permanently become deformed from its original shape. That's a process that takes up energy, whereas something that's elastic is pretty much instantaneous and you get the same amount of energy out as you have put in. Let's return to this sketch now and add one more thing here. Add Poisson ratio, nu. Unfortunately, that's the same notation as for frequency sometimes, so be careful of the context. And what that is, it's a monitor of how much the shape changes as you elongate it. So does the sample become like this as it stretches? Does it become thinner or not? And so now that change right there, that would be delta x. And so the Poisson ratio is defined as the strain in the x direction divided by the strain in the z direction. And because strain, again, is delta x over x0, and for the other direction it would be delta L over L0, and I'll add the delta L over here. Note that L is getting bigger in the z direction, but x is getting smaller horizontally. And so if we leave the definition like this, the Poisson ratio would be negative. Well, people don't want to bother with that negative number, so what you do is you negate the definition, throw in a minus sign there, and it becomes positive. So many materials have Poisson ratio around 0.3, meaning they get a little bit thinner as they're elongated. Rubber band might be about 0.45 or 0.5, and the range, I believe diamond is the lowest, so that's 0.16 and goes up to about 0.5. In summary for this lesson, we've spoken about several different terms that we'll use in upcoming lessons. The work of adhesion is a measure of the strength of the surface forces that act between the tip and the sample per unit area. The contact radius gives us insight into how to calculate that contact area between the tip and the sample. The reduced radius reveals the influence of the sample topography on that measure. Stress, strain, elastic modulus, that's all about the bulk stiffness of a material. I also mentioned plasticity in there. And the Poisson ratio is a measure of how much a sample's shape changes as we elongate it.